Hi, every student. Okay, good afternoon. Now it's afternoon. Okay, I think good evening. Good evening to all the students. Okay, so for the student, they wait so long about the 5.1 until 5.4 for the formative practice. Okay, so now I go to discuss about this practice and give you the some example answer lah. Okay, let me go through about that. Okay, so we go through to the first part for the 5.1 first. They're about the waiver. There's about the fundamental of the waiver. Let's see what is that. Okay, first one about the formative practice 5.1. They show you the graph. Okay, now the graph is a displacement versus the time. Okay, displacement versus time. So from here, they show you the amplitude. From here, we cannot see about the wavelength. You only can see about the periods. Okay, because the horizontal is a time taken. So the first one, they ask you what means of the amplitude. So we just give the definition. Amplitude, we either read at the top maximum or you read at the bottom also can. So the first one, the definition for the amplitude, there's a maximum displacement from the equilibrium position. So the center line we call equilibrium positions. Okay, determine the periods. So the period we just find one complete oscillations. Okay, one means of one complete oscillation, that means where you start. Okay, example, I start from here. It's a bottom that start from the 0. So I make one complete oscillation. I need to go up until the crest, then I come down. Okay, until 0.2 actually is half, that not full. So you want to produce the full one, so that means you need to continue. 0.2, continue to draw at the bottom, then come back. So this one we call one complete oscillations. So the period must be 0.4 seconds. Okay, after you get the period, that means you can find the frequency lah. We got formula. Okay, the frequency equal 1 over periods. So from here, we just apply 1 over 0.4. So the final answer is 2.5 hertz for the frequency. If you want to write the unit for the frequency is per second, that's still okay. They're also correct. Okay, then we continue to the second question for 5.1. We compare the contrast progressive wave and also the stationary wave. Okay, progressive means continuous. The wave you produce continuous. So that means you listen the sound, the continuous sound. So a progressive wave, there's a wave where the wave file, they move with the time along the direction of the wave propagation. So that means the wave propagate, they will work, they will move together. Okay, move together with the wave propagate. So that means you will continuous to listen. Okay, maybe sound wave, that means you continuous to be listen the sound. Okay, if I say stationary wave means they will stop. Okay, a stationary wave, there's a wave where the wave profile that does not move with the time. So when the time just pass, the wave then finish. There's no need to be continuous. So this one is a differentiate between the progressive and also stationary. Okay, number three. Number three is a calculation. Number three, no calculation. They just ask you about the type only. Okay, they show you about the slinky spring being moved forward and backward. So you can see this one don't have any crest, don't have any trough. They just got closer and further, closer and further. So from here, they ask you what time of the wave they produce the slinky spring. So your answer should be longitudinal wave. Okay, this one is a parallel. Okay, the particle vibration and the direction of the wave moving them both in parallel. So this one we call longitudinal wave. Okay, then we continue with number three. You need to mark. Okay, mark the X at the refraction part. So refraction means what? Far away. Okay, when you see the spring, the far away part by part, that one we call refractions. When you see the closer each other, that one we call there's a compression. So from here we can mark lah any place. Any place you can see there's a refraction, then you just mark it. Okay, from here we can see there is a this part also can, this one also can, then this one also can. Okay, so that means either one you go to mark, there's a X, there's a rare fraction, then the answer is correct. Okay, C is what is the wavelength? Okay, what is the wavelength? So from here, the wavelength is they want you to find what's the wavelength. Actually, they want to find about calculations, is it? So if the question what is the wavelength, so we just answered it because the question provide 10 cm. So we just answer by calculations. Okay, wavelength lambda equal 10 over 2. Okay, you can answer by definition now what means of the wavelength. So wavelength actually is a distance between two consecutive crests. Okay, or you can say about the distance between two consecutive truth also can. Okay, so from here you can do the calculation. If they show about 10 cm, then we do the calculations lah. So from here 10 cm actually inside got how many lambda, how many wavelengths, so we can count like this. Okay, we need to show the drawing. Okay, so if I start from here, okay, so this one's a compression, then I go to find the successive compression, then should be this one. Okay, continuous until this part. So actually they got one and also the two wavelength. Okay, so from here that means you need to do the calculation for the 10 over 2. When I just 10 over 2, there's a 5 cm. So that means the lambda should be 5 cm for these situations. Okay, then 5.1 we finish. Then we go to 5.2 about the damping. Okay, first one they ask what means of damping. So damping, everybody know lah. Damping is a process. They will slow down. Finally, they will stop. Okay, so damping, there's a process whereby the oscillation they will die down. Okay, due to the loss of the energy to frictional forces. Okay, we got external, we got internal friction. Okay, external, sure, there's an air resistance. Then the internal is a molecule. So after that, they will cause us about the object, slow down, finally they will stop. Okay, so this one is a definition for damping. Okay, now you need to sketch about the graph displacement against the time for experiences damping. So remember when you draw the graph, okay, they're just like the sinusoidal graph. Okay, the amplitude just keep dropping. Okay, how about the distance between the wave to another wave? Actually there's no changes. Okay, we see how to draw. So this one is the answer. You can find out the amplitude keep dropping. Okay, if you don't know how to draw, you need to sketch. You need to sketch one of the curve. If you sketch the curve, that means you more easy for you to drag. Okay, to drag the graph. Okay, drag the wave pattern, make the amplitude keep dropping. Okay, but you go to observe, this one is a distance. Okay, every distance of the wave, okay, you can say lambda lah. Okay, if I start from 0, this one should be the this one is a time, is it? So time we call periods lah. Okay, the period is always the same. Okay, the distance always the same. We don't have any make it become smaller. So better you go to jot. Okay, make a note. Okay, every part you make a note. So when you draw, there's a more easier for you. If not, you go to make it become shorter, you make it become closer one. Okay, so this one is one of the tips to teach you how to draw the damping wave pattern. Okay, then we go through to the 5.2, continue with number 3. State the 3 example, the effect for the resonance in our daily life. Okay, resonance, remember when they just achieve match by the natural frequency and also the external frequency. When they just match together, they produce a maximum amplitude. The one we call resonance. Okay, in our daily life, actually we got for certain situations they got resonance, but we not realize. Okay, actually lah. So from here we can see some example, 3 example. Okay, first one is a washing machine. So you can find your washing machine, the third round, if I'm not mistaken, the third round, when they just spin, they will spin very, very high, faster. Okay, high frequency and also faster. Then you can listen the sound, suddenly they become very louder. That one we call they achieve the resonance. Okay, resonance, the force to spin, and also the natural frequency of the washing machine. Okay, number 2 is a wind music instrument. So that means when you play the instrument, when you listen the voice, they will just produce as a very sweet, okay, very nice. That means they achieve the resonance. So that means when you play, you're not a professional go to play. That means you produce the voice, where produce the sound just like the noise. That one we didn't call it as a resonance. Okay, that one we call it as a disturbance. Okay, so after that we got turning the tuning circuit for your radio set. Your radio set, you have to set the FM, is it? So you find it, you go to different state. Example, from the Malacca, you want to go to KL. So when you just on the way to go, so you find it, the radio set that will changes FM, is it? So from here you can listen, but you go until KL, that means you need to change another channel. Okay, another channel, but still the same channel should be different. Channel should be same, but you need to adjust the number is a different. So that one we call it resonance. So you want to achieve match resonance, that means you need to changes some of the frequency. After that, then you become match. So this one is a 3 example for the resonance in our daily life. Okay, how can the resonance overcome the damping? Okay, resonance can overcome damping. How come? So you see number 4, the effect of the damping that can be overcome by apply the periodic external force. So damping is slow down, is it? So that means I apply the force lah. When I just apply the force, that means I can overcome the slow down. I can make the object keep swinging. Okay, so from here, the periodic of the external force, they transfer the energy into the oscillating system. Because damping, they will lose the energy. So when I just extra force, I go to acting to the situation. So that means now the process, the continuous got energy because I add it. They never lost already. So from here, this one, we call it they overcome the energy loss. When the periodic force is applied in an oscillating system at its natural frequency, so the oscillating system is said to be resonant. So example, just like the swing at the playground. So that means when you just swing, you never extra force to add to the swing. That means you find it finally the swing will slow down and stop. So from here, when I just push again the swing, so they will continue to be swinging. So when I just slow down, when I add a force again, they will continue to swing. So that means I make it reduce the force, the energy loss. Although they lost, then I add again the force. So that means finally the damping can be overcome. Okay, by using the extra force acting to the system. Okay, so 5.2 we finished. Then we continue with the 5.3. 5.3 is a reflection. So that means when the liquid, or you say the sound, or you say about the light also can, when they just enter the obstacle, something is blocking lah, so they will reflect it, come back. So this one we call refractions. So 5.32, they want you to draw the wave front and the direction of the refraction of the water wave. So the first one direction they go in, this one we call incident wave. Okay, this one is a direction. Then the horizontal, that one is a wave pattern. So remember the wave pattern and also the incident wave must be 90 degrees. Then this one should be the normal lah. Normal must be 90 degrees with the obstacle. So incident angle how many? Actually, incident angle is 20, not 70. Yeah? This one we call incident angle. Incident angle must be between. This one we call incident angle. Okay, they must be between the incident wave and also the normal. We call that's an incident angle. Okay, now we go through to the drawing. Okay, we need to show how they go to reflector back. So the first one, we need to draw the arrow. Must draw the arrow before you go to draw the wave pattern. So follow the law of refraction. Incident angle 20. So refracted angle also almost is 20 when you draw. Okay, if you can using protractor. to make sure there's a 20 degrees. So from here, we just draw. Okay, so I find it. This one is a refracted directions. Then after that, I go to draw my wave pattern. Make sure the wave pattern, there's a red color, is it? The red color and the black color must be in 90 degrees. Okay, 90 degrees. So another one you need to attention a bit. That one is a wavelength. Blue color and another blue color, that one is a lambda, is a wavelength. So after reflected, the wavelength also must be same. Okay, no changes. So when I just draw the second line, I want to make sure the same like the original. Okay, let's say this one is 0.2 cm. This one also must be 0.2 cm. So you continue to draw 3 to 4 waves, then enough already. No need to draw so much. Okay, so this one is the number 1 answer. Okay, then we continue with number 2. Number 2 is a calculation for reflections. Okay, remember for sound wave, okay, normally they want you to find about the depth. Okay, the depth of the sea bed. Okay, remember the depth is only one way. Okay, for refraction, actually the process is two-way because you send and come back. So that means the time taken already is two-way. Then the velocity, when they just send, they're also in a two-way. But the question, always they ask that. That is one way only. So that means after that you get the answer, you need to divide by 2. That one is the calculation for refractions. Okay, so this one is the formula for refraction. V, velocity, send and back. Okay, time taken also is send and also back. But the distance depth only is a 1. So from here, everything is a two-way. So you need to add 2 here. Okay, add the 2 here. So you find the answer 1,500. This one is a velocity. Multiply with the time taken when I just send back. So I need to divide by 2. Remember, must divide by 2 because there's a two-way. I just want to find that. So after you divide by 2, I find it. There's a 45 meter. Okay, so this one is the question number 2. Okay, then we go to 5.4. Okay, the first one, they ask you what phenomena of the wave that happen when the sea wave are approaching to the beach. So everybody know when they're approaching to the beach, the deeper already decreases. At the middle of the sea must be deeper. When they're near to the beach, you find it, they become shallower. So from here, the phenomena we're using sure is a refraction. F-R-A-C. Okay, then after that, you need to explain your answer with the help with the diagram. Okay, now we go to start. Okay, the first phenomena we're using, that's a refraction of the sea wave. Okay, we're going to see the diagram. Okay, this one is an example for the diagram. When it's just near to the gap and bay, okay, we see what happened. First one, I want you to observe the wavelength. Okay, at the middle of the sea, the wavelength is bigger because there's a deeper. Okay, when deeper, the lambda should be higher. So when it's just near to the beach, okay, we separate by 2 parts, gap and also the bay. When they're near to the gap, can you see the wavelength become smaller? Okay, compared to the bay, the wavelength bigger a bit. So from here, we need to relationship the the depth and also the wavelength. Okay, we need to explain. So from here, when the wavefront, okay, wavefront, you can say normally the same meaning just like the wavelength. When the wavefront of the water propagate to the gap, when they propagate to the gap, just go through the gap, the speed of the water wave will decreases. Okay, the speed just come to the gap that will decreases. When it just velocity decreases, understood, lambda also decrease. So they say the wavelength becomes shorter. So another way, wavefront when they're just approaching to the bay, okay, to the bay, after that you find it, the speed is higher a bit compared to the gap. Okay, you didn't compare the bay and also the middle of the sea. No, we just compare the bay and also the gap. Gap becomes speed slow. Okay, bay fast a bit. So from here we can find it, the wavelength at the bay is longer a bit. So from here, gap and bay, different of the wavelength. Finally, you can see the wave pattern. They follow the shape of the beach. Okay, follow the shape of the beach. So you find it the wavelength at the gap become closer. When at the bay, further a bit. So that means they're just like a curve. Okay, compared to the deep sea is a flat only. So this one is a differences. So this causes the wavefront to curve and follow the shape of the shoreline. So this one we call shoreline. They follow the shape. Okay, so this one we need to explain when the wave just near to the beach, actually what happened. Okay, so we go through to the number 2. Number 2 is calculations. From here, the question they say the water wave of the frequency 10 hertz approaching from the deep. This one is a deep. Okay, after that, to the boundary of the shallow region, there's a PQ. Speed of the water in the deep is a 30 cms -1. So they give you all the info for the deep area lah. So you need to calculate the wavelength. Okay, wavelength for the deep region. So the formula we just using V equal F lambda. Okay, when you want to find about the lambda. So we just apply for the info first. Remember, student, info is very important. You need to jot down all the info before you want to start to do the calculations. So from here, I just jot down. Frequency is a 10. Okay, V1. 1 is stand for deep area. 30 cm S -1. Okay, lambda 1 we do know. Lambda 1 is a deep area. So lambda 2 means there's a second question. There's a from the shallow region. V2, we don't know. So the first one, we go to settle the lambda 1 first. Okay, we just apply V equal F lambda. Okay, V is a 30. Then the frequency is a 10. So lambda, we get it. The answer is 3 cm. Okay, at the deep region is a 3 cm. So we compare lah. Deep region 3 cm. Then the shallow region 1.5. So logic lah. Is it deep area? The wavelength must be longer. Okay, the second one, we need to do the calculation for the wave speed when it just enter to the shallower region. So we're still using the same formula. V equal F lambda. Okay, now we need to count is a V. So we just apply the frequency. So you can observe, we got one of the physical quantities is totally no changes. That's a frequency. I don't care you are deep or you are shallow. When it just the liquid just pass through, the frequency is no changes because they come from the same source. Okay, example, this one from the river tank. River tank from the same motor, vibration is the same. So that means the frequency is always constant. So from here, we need to find velocity. So we just apply frequency is a 10. Then the lambda, just now they told you there's a 1.5 cm. So final answer, the speed is a 15 cms -1. So that means at the shallower region, they become slow down. Okay, so this one is what about the question number 2. Okay, then we go to following C. Okay, the arrow, draw the direction of the propagation of the wave in the shallow region and then sketch the wave front of the water wave refracted in this one region. So that means you need to draw lah. Okay, this one is a deep region, then this one is a shallow region. So we need to draw first. Okay, we draw refractions. Okay, they will closer. This one is a deep, then this one is a shallow. They will bend towards the normal. Okay, pans towards to the normal. Then from here, after they bend towards to the normal, you can see the incident angle and the refractor angle. Incident is bigger than the refractor. Okay, so from here, we continue to draw the wave pattern. So the wave pattern we just show. This one is the wave pattern. There's a 90 degrees with the arrow. 90 degrees with the arrow. So you can find it. They join the line. Red color line, I draw by dotted line. They join with the blue color line. Okay, the blue color line is just now. They're not yet complete. So I go to join the line. So I continue to draw. Okay, So you can see the second one also continue to drop. So you find it, the distance between the two red color line is become smaller. Okay, the wavelength becomes smaller already. So I continue, then I continue, then I continue. So you find it, the wavelength, the distance become smaller. Okay, make sure there's a 90 degrees. Okay, so we continue. Okay, so we just draw it. So make sure you go to continue the line when it just not complete. Okay, then after that, compare the frequency, wavelength, and speed. Okay, before and after. So in the deep region and also shallow region, we compare frequency, wavelength, and also the speed. Okay, first one, frequency constant. Just now I told you, frequency in the deep and shallow must be constant. Okay, number two, you see the wavelength. Wavelength at the deep sure bigger. Okay, at the shallower become decreases. And the last one should be the speed. When I go to the shallower region, the speed becomes slow down. Deep region, they become fast. Okay, then we just finish. Okay, so this one is a 5.1 until 5.4. So the coming soon, I will upload about the 5.5 until the 5.7. Okay, so hopefully the student you understand what I present just now, and also thank you for your watching. Okay, see you for next time. Okay, bye.